Welcome back to Bite-Sized Breakthroughs. Today we're diving deep into a fascinating research paper titled Unmasking the Lottery Ticket Hypothesis: What's Encoded in a Winning Ticket's Mask. This paper delves into the workings of a crucial technique in deep learning called Iterative Magnitude Pruning, or IMP. Dr. Paige Turner, the lead researcher on this project, is with us today to guide us through the intricate details. Dr. Turner, thank you for joining us.
It's my pleasure, Alex. I'm excited to share our findings with your listeners.
Before we get into the specifics, let's set the stage. Professor Spectrum, who's a leading expert in the field, can you give us some context on the challenges faced in deep learning and why this research is so crucial?
Well, Alex, modern deep learning is powered by these massively complex neural networks. They're often over-parameterized, meaning they have far more connections and weights than strictly necessary. This leads to massive computational costs and memory demands, especially when deploying these models on devices like smartphones or other resource-constrained environments.
That's where techniques like iterative magnitude pruning, EMP, come in, right?
Exactly. The goal of IMP is to find these so-called winning tickets, highly sparse subnetworks within the larger network that can be trained to achieve the same accuracy as the full, dense network. Think of it as finding a smaller, more efficient blueprint for the original complex structure.
So, Dr. Turner, what are the key contributions of this paper? What new insights did your research team uncover?
Our paper delves into the why and how of IMP's success. We uncovered several crucial insights. First, we discovered that the mask generated by IMP, the key to determining which weights to prune, doesn't just randomly zero out connections. It actually identifies a specific subspace within the weight space, a kind of shortcut that intersects with a sweet spot of matching solutions.
A sweet spot. Can you elaborate on what that means, Dr. Turner?
We call it a linearly connected sublevel set, or LCS set for short. Imagine the error landscape, which represents how the network's performance changes based on its weights. The LCS set is a region where all the points, different weight configurations, have roughly the same error, and you can move between them without encountering major error barriers. So the mask helps guide the training process towards this area of optimal solutions within the sparse subspace.
That's fascinating. It's almost like the mask acts as a map, pointing the training process in the right direction.
Precisely. But there's another key element, the role of SGD, or stochastic gradient descent, the workhorse of neural network training. We found that SGD is incredibly robust to perturbations, even significant ones, within this LCS set. So even if the network is nudged off course by the pruning process, it can still find its way back to the optimal solutions.
So the mask tells you where to look, and SGD's robustness ensures you'll find something good, even if you get slightly lost along the way.
Exactly. It's a beautiful interplay of information and resilience.
Professor Spectrum, this is starting to sound incredibly elegant. How does this compare to previous approaches to network pruning?
Well, Alex, earlier methods often relied on one-shot pruning, where you try to remove a significant portion of the network's connections at once. But this paper highlights the importance of iterative pruning. Pruning a small fraction of weights, retraining, and then repeating the process. This iterative approach allows for a more nuanced understanding of the error landscape and leverages the information encoded in the mask more effectively.
So, Dr. Turner, what about the role of the Hessian, a mathematical concept representing the curvature of the error landscape? How does that factor into IMP's success?
The Hessian is crucial because it tells us how much the error landscape changes with respect to small changes in weights. We found a clear connection between the Hessian's eigenspectrum, essentially a fingerprint of the curvature, and the maximum pruning ratio you can apply at each iteration without sacrificing accuracy. A flatter landscape with more small eigenvalues allows for more aggressive pruning, while a sharper landscape requires more careful pruning.
So you can't just go crazy and prune a huge chunk of the network at once. The curvature of the error landscape puts a limit on how much you can prune at each step.
That's right. It's like navigating a bumpy terrain. You need to make smaller adjustments if the ground is uneven.
That makes sense. And what about retraining? What's its role in finding these sparse matching networks?
Retraining is essential because it helps to re-equilibrate the weights. When you prune, you're changing the distribution of weights. Retraining allows the network to readjust, creating new small magnitude weights that can be further pruned in the next iteration. This is why strategies like weight rewinding and learning rate rewinding are so effective, as they encourage this re-equilibration, whereas simply fine-tuning the network doesn't achieve the same result.
So it's not just about getting rid of unnecessary weights, it's also about reshaping the network's structure to make it more amenable to further pruning.
Exactly. It's like sculpting a masterpiece. You need to refine and adjust it over time to reach the final form.
This is all very detailed, Dr. Turner. Let's talk specifics. Can you tell us about your experiments, the data sets you used, and the results you observed?
We used a variety of standard benchmark data sets, CFAR 10, CFAR 100, and ImageNet, and tested our ideas on ResNet architectures, specifically ResNet 20, ResNet 18, and ResNet 50. We found that when we applied IMP and retrained with either weight rewinding or learning rate rewinding, we could achieve significant sparsity levels while maintaining the same accuracy as the dense network. For example, on a ResNet 50 trained on ImageNet, we could reduce the number of weights by an order of magnitude without any loss in accuracy.
That's a remarkable improvement. Did you find any limitations to your approach, Dr. Turner?
Of course, there are limitations. Our analysis relies on approximating the error landscape as a quadratic function, which simplifies the real-world complexity of these landscapes. We also need to investigate the generalizability of our findings to other pruning algorithms and datasets.
Prover Spectrum, what are your thoughts on these limitations and potential future directions for this research?
It's important to acknowledge that the quadratic approximation of the error landscape is a simplification. We need to explore how these insights hold up in more complex and realistic landscapes. Furthermore, while the paper provides a strong framework for understanding IMP, there's potential to investigate the generalizability of these findings to other pruning techniques, potentially leading to more versatile approaches to sparse network design.
What are the broader implications of this research, Dr. Turner?
This research has several significant implications. First, it provides a stronger theoretical foundation for understanding and improving network pruning techniques. Second, it underscores the importance of SGD robustness and opens up possibilities for developing more robust and efficient training algorithms. Third, the link between the Hessian eigenspectrum and pruning performance can guide the development of adaptive pruning strategies that dynamically adjust pruning ratios based on the error landscape's geometry. Finally, our insights into retraining can lead to more efficient and effective techniques for finding sparse, high-performing networks.
This research has the potential to revolutionize how we train and deploy deep learning models, especially in resource-constrained settings. Prover Spectrum, what are some potential applications of these findings?
The applications are vast. We can imagine using these techniques to build smaller, more efficient models for mobile devices, edge computing, and other scenarios where computational resources are limited. Furthermore, these insights can be applied to optimize the training of sparse networks in areas like natural language processing, computer vision, and robotics.
This is a truly groundbreaking study, Dr. Turner. To summarize, your research unveiled the intricate interplay of the pruning mask, SGD robustness, the Hessian eigenspectrum, and retraining strategies. By dissecting the mechanisms behind IMP, you've provided us with a deeper understanding of how to find efficient, high-performing sparse networks. Thank you for sharing your insights with our listeners.
It was a pleasure, Alex. I hope our work inspires further advancements in the field of deep learning.